A very good day I bid to Dr. Ayub and Dr. Royub. Today, my team is going to present on the presentation of the Plant Design Project 2, namely Sulfur Oxide Emission Reduction of Thermal Oxidizer Flue Gas. We are from Group 17 and we consist of Prem Raj, me, myself, Wong, Wignish, Lim Hui Kiat, and Rashmi Transiwom. Our agenda would consist of an introduction by Prem Raj and Pdp Ii review, started off with a conceptual design by Wignish and Prem Raj. Next, heat integration by me, Wong Yongshen. Process instrumentation and control by Lim. Process safety loss prevention by Mitra. Plant layout is also by Mitra. Next agenda will be waste treatment by Wignish and Wong, which is me, and economics evaluation by Lim and Prem, and our project is concluded by Mitra. And now I'll pass on the floor to Prem Raj.
Hi everyone, I'll be presenting on a brief introduction on the plant design project. So we was given a problem statement whereby we have to reduce the emission of the SO2 and CO2 that coming out from the thermal oxidizer, as well as to change it into a value added product. So as you can see, these are the parameters that is shown in the slide. Moving on to the team's objective, we try to come up with a conceptual design in order to meet the client's request, as well as utilize the energy optimization via integration to reduce the energy cost. Okay, this is our product market analysis, whereby we did a study and we found out for SO2, if the value product ammonium sulfate gives us a higher demand, and for CO2 is methanol. The proof is on the slide. Moving on to the process screening of SO2 and CO2. These are the how we determine which kind of process we should do to scrub the SO2 and CO2. And next for SO2, we have this ammonium scrubbing and Belmont process. These are the two alternatives. And based on the study on the EP comparison, we have found out that ammonium scrubbing has a lesser EP, so that we go for that choice. For the value product, we did the process screening, and we found out that for the ammonium sulfate is via forced oxidation, and for methanol is a direct hydrogenation. And for SO2 removal, as you can see, this is a specific whereby the flue gas enters here and it reduces temperature using heat exchanger via cooling water. And when you go into the tower, there will be an inlet of ammonium hydroxide in the top of the tower, and in the bottom there will be the product ammonium sulfide, and there will be a rich gas on top, which is CO2.
Next is the process flow diagram for ammonium sulfate production. For the ammonium sulfate production, ammonium sulfide from the SO2 absorption tower will be mixed with air in the mixer and will be flowed into the oxidation reactor operating in 1 bar and 308 Kelvin. Ammonium sulfide will be oxidated to ammonium sulfate based on the formula below, and the stream will be flowed into the cyclone for the ammonium sulfate to be separated. The excess air will be released and the excess water will be recycled into the ammonium hydroxide tank.
The CO2, we have a separation process and we have to study it, and we found out we have this two process, and we found out that since we are using for SO2 is ammonia, so it's better we use same process for CO2 as well. So we come up with this idea whereby this is the process flow diagram. When there's a CO2 is the rich gas coming into the absorber, we use the same process whereby ammonia comes going inside and be absorbed and goes to the regeneration column. We get the pure CO2 for methanol production.
Process flow diagram for the methanol production. The CO2 gas from the stripper will first be flowed into the compressor to increase the pressure before it is mixed with hydrogen in the blender. It is then flowed into the methanol reactor, which is operating at 50 bar and 493 Kelvin, to produce methanol and water based on the reaction below with an efficiency of 60%. The solution will then be flowed into the wash column and then to the distillation column to produce pure methanol with a purity of 99.9%. The purged water will then be recycled back.
As you can see in the process flow diagram, this is the SO2 ammonia scrubbing area, and this is the CO2 ammonia scrubbing area, and this is the regeneration column, and this is the oxidation whereby ammonium sulfide is oxidized to ammonium sulfate. And moving on to the second sheet, whereby this is the methanol production plant.
Thank you, Wignish and Prem, for the presentation about conceptual design. Moving on would be the heat integration and the process flow diagram based on the PDP-1. So heat integration is important in order to reduce the utility of our project to as low as possible. So heat integration is started off with the calculation of heat capacity by multiplying the mass flow rate and specific heat capacity with the data extracted from ICON. And then the pinch temperature is determined using a table algorithm problem and the temperature cascade as well. And after that, a heat exchanger network is developed, guided by maximum energy recovery framework, which means to reduce the utility to as low as possible, as well as following the rule of thumb. So our heat integration is divided into two sections, the ammonia scrubbings and the methanol production. So for ammonia scrubbing, this is the network of the heat exchange and heat integration. And based on the heat integration, it is seen that the number of cooler is not reduced, and the number of heater is reduced to 0. And the heating requirement reduced by 100%, and the cooling requirement is reduced by 30%. Totally, the total energy recovered is 46.15%, which is almost half the energy recovered. The next heat integration will be the methanol production, where this is the network for the methanol production heat integration. So although no cooler and heater is reduced, the heating requirement is reduced up to 96.21%, and the cooling equipment is reduced up to 85%, and thus there's a total energy recovered of 90.68%, which is significant. So this is the PFD before HI with coolers and heaters present for ammonia scrubbing, CO2 scrubbing, and forced oxidation. And this is the PFD for methanol production before heat integration. And this is a PFD for after heat integration with the presence of heat exchangers for both PFDs. So that's it from me. I will pass on the floor to Lim. Thank you very much.
Next, I'll be presenting on the instrumentation and control strategy that are used in this project. So there are three types of control strategy. The first one is a basic one, which is feedback control, and the higher level one is the ratio and cascade control. In the equipment of the absorber column, we take the example of SO2 absorber, and we use ratio control to maintain the percentage of SO2 removal by manipulating the lean aqueous ammonia flow rate. And we use feedback control to control the pressure and also liquid level in the column by manipulating the outlet flow rate of fan gas stream and also outlet flow rate of rich ammonium sulfide streams. And for distillation and stripping column, we take the example of methanol distillation column. We use feedback control strategy to control the inlet flow rate, pressure, liquid level, and also temperature in the distillation column. And we're manipulating the inlet flow rate, condensate cooling water inlet flow rate, reboiler bottom stream outlet flow rate, and also reboiler stream inlet flow rate. And for reactor, we are taking the example of oxidation reactor. The ratio control is used to maintain the stoichiometric ratio of air and ammonium sulfide fed into the reactor, and we are manipulating the inlet flow rate of ammonium sulfide. And we use feedback control to maintain the temperature and liquid level in the reactor by manipulating the inlet flow rate of cooling water stream and also the outlet flow rate of ammonium sulfate.
Now I'll be presenting on the HAZOP study. So HAZOP is used to evaluate the risk and hazard that may occur to people, environment, asset and reputation. It is used to identify the design, operating and quality problems related to the process. Guided words are used in HAZOP's sheet. 3 knots were selected for our HAZOP study, which is number 1, methanol separation from water, number 2, sulfur dioxide removal from flue gas, and last 3, carbon dioxide hydrogenation to produce methanol. This is a sample of HAZOP sheet. So a HAZOP sheet has parameters, guide words such as no, less or more, deviation, causes, consequences and action required. I'll be explaining on how the HAZOP sheet works. So now our first parameter is temperature. The guide word that we will be using is either less or more. For less, the deviation that occurs is less operating temperature, which is below 220 degrees Celsius. So what are the causes is that TT326 valve failed to open and TT336 valve failed to open. The consequences is that there is no conversion of methanol or lesser conversion of methanol. And the second consequence that happened is the production will be halted. Therefore, the action required is low alarm needed to be installed. Second is periodic inspection and maintenance need to be done in order to prevent the valve from fail open. This is an example of our plant layout. Note that the exits are highlighted and the green road shows the closest route to the assembly point. Some of the plant safety features are fire extinguishers to put out small fire, blast valve to minimize impact from fire and explosion, fire alarms to alert employees during emergency, fire water system where the water is used for emergency, process shutdown where part of the process will be shut down. Lastly is the emergency shutdown where the whole plant will be shut down due to any hazard or risk that may occur.
I am now going to talk about the waste treatment process. This process is very important to ensure that the environment is not being polluted by this process. Besides that, waste treatment is also vital because untreated waste will deteriorate our water quality and our air quality. Laws and regulation limits. Malaysian government has begun paying attention to environmental concerns, and the nation has witnessed various environmental programs, laws, as well as creation of new government ministries to curb the environmental problem. Through the enforcement of various laws in Malaysia, all industry and organizations involved are to follow the rules enforced strictly to maintain environmental sustainability without compromising future generations' raw material sources. The laws that have been imposed are such as Environmental Quality Act 1974, Malaysian Carbon Reduction and Environmental Sustainability Manifest, Environmental Quality Regulation 2005, Environmental Quality Industrial Effluent Regulations 2009, and the Environmental Quality Clean Air Regulation. The laws and regulations to limit the amount of waste being released by any industry is stated as below. For solid waste limit, it is based on the Environmental Quality Scheduled Waste Regulation 2005. For liquid waste limit, it is based on Environmental Quality Industrial Effluent Regulation 2009, and for gas waste limit, it is based on Environmental Quality Clean Air Regulation 1978. For solid waste, the waste identified is ammonium sulfide, which is produced from forced oxidation reactor through stream number 104, and the fraction is about 0.0073, and the molar flow is about 0.83 kmols per hour. The treated method for this solid waste is done by Quality Alam Sdn Bhd. Based on Environmental Quality Scheduled Waste Regulation 1989, it is required that scheduled waste be treated and disposed of a facility be approved by the Department of Engineering, DOE. The Quality Alam Sdn Bhd is responsible in handling the scheduled waste. Before the waste is sent to Quality Alam Sdn Bhd, the waste should first undergo the filter press to remove the water content, which is in slurry form. The water is then sent to a water treatment plant within the facility and treated accordingly to the standard in safe and practiced manner. So now I pass the floor to Nicholas. Thank you.
Thank you, Vignesh, for the presentation about solid waste strategy as well as the law identification. Moving on to the next one would be the gas waste identification from our project, which is carbon monoxide, CO2, hydrogen and methanol from stream 209 and stream 315 as tabulated over here. So based on our gas waste identification, we move on to our strategy treatment, which is the flaring process, which is a safe option in order to dispose the waste. The waste are burned under controlled conditions, and they are usually reacted with the atmospheric oxygen to form CO2 and water. And the conversion of the gases to CO2 and water is generally over 98%, which is very high. And that's all for the gas waste. Moving on to the liquid waste strategy, we first all started with the identification of the liquid waste stream properties through the distillation column outlet as tabulated over here. And we move on to the stream identification, where we identify the components, which is a methanol, which is 1% in this stream. So based on that, we move on to getting the standard for the boiler feed water discussed by SPE, which means that the liquid waste being treated must meet these requirements before being discharged into the environment. So based on our liquid stream identification, the selected treatment method for liquid waste would be activated sludge process in order to remove the organic matters, in this case the methanol. And due to its a low installation cost and the operating principle is simple and practical. So this is the flow sheet of our liquid wastewater treatment plant. Started off with the pre-treatment, the primary treatment, secondary treatment, and lastly the tertiary treatment. So the influence started off by going into the screening, where large solids such as rocks are removed, and it is undergone a grid chamber as well, where finer solids such as sand is removed. And then it undergoes the equalization tank, where the flow rate is equalized to overcome the flow rate variations. And after that, dosing tank is installed to maintain the pH of the influence before going to the primary treatment. And the primary treatment is usually is for the removal of total suspended solids from the influent, such as heavy toxic metals, usually through physical methods such as sedimentation, as well as chemical methods such as alum for coagulation. And after the primary treatment, the influence is moved into the secondary treatment, which is through the activated sludge process in the aeration tank. So in the aeration tank, the microorganisms will be consuming the organic matter, which is methanol, and they will form activated sludge and accumulate at the bottom. So this activated sludge would then be put into the clarifier to separate the activated sludge from the remaining influent. So from here we can see that a part of the activated sludge is recycled back to the aeration tank in order to maintain the food to microorganism ratio, to maintain the efficiency of the aeration tank. The rest of the activated sludge is sent to the sludge dewatering and disposal, which is known as a waste activated sludge. So after the activated sludge process, the influent is further sent to the tertiary treatment, where the remaining suspended solid and also the organic matter is removed. So it first started off with the sand filtration, where finer solids are removed, and then it undergone the activated carbon absorption is also installed in order to remove the remaining organic matters. After that, the effluence is ready to be discharged back into the environment. And that's all for our waste treatment strategy. Thank you very much, and I move past the floor to Lim and Prem.
Next, I'll be presenting on the economic evaluation of our project. So there are two assumptions that has to be made before we proceed. First, we assume the conversion rate of USD to Ringgit Malaysia is 1 to 4.2. Second, we assume the plant operates for 330 days per year with a lifetime of 15 years. First, we need to calculate the capital investment, also known as CAPEX, by finding the value of fixed capital cost and working capital. FCI can be calculated by first calculating the purchase cost of equipment. The list of table here show the equipment that are present in our plant, and we have a total purchase cost of 22 million. Next is the physical plant cost, where we can get the value by multiplying the direct cost factor with the PCE value that we obtained previously. As we can see, F5 to F9 is not considered because our fuel gas treatment facility is just an addition to the existing plant, so it is not considered. And the PPC that we get is 53 million. Next, to calculate the fixed capital cost, we take the PPC value previously and multiplying with some direct cost factor for constructions as shown in the table here, and we get a FCI of total of 77 million. And to calculate the working capital, we assume that it is 15% of the fixed capital cost, and we get a working capital of 11 million. So back to the CAPEX formula, we sum up the fixed capital cost and working capital, and we will get a value of 88 million of CAPEX. Next is the annual operating expenditure, or also known as OPEX. OPEX consists of two items, which are direct operational costs and indirect operational costs. For direct operational costs consists of fixed operating costs and also variable operating costs. Fixed costs include the maintenance costs, operating costs, and so on. And variable costs consist of raw material costs, utility costs, and so on. And Indirect operational costs mostly consist of the R&D costs and excess expenditure in our plant. So the total OPEX for our plant is 542 million per year. So previously we discussed about the expenditure. Now we'll talk about the revenue that could be generated by selling our byproduct, which are methanol and ammonium sulfate. So the total revenue that we could achieve is 603 million per year, and we can calculate the gross earning or net profit by subtracting the OPEX from the total annual revenue, and we'll get a total revenue of 60 million per year. Next, the rate of return is used to determine the economic performance of our plant. The ROI is calculated by using the cumulative net cash flow at the end of the project divided by the plant life of 15 years multiplied with the total capital investments. And the rate of return of our plant is 38%, which is higher than the minimum acceptable rate of return of 20%, which means our project is profitable. And from the graph of payback period, we can see that from year -2 to 0, this is where our plant is constructing and we are spending the cost that we calculated in capex. And from a year of 0 to 15, the plant start to operate and generate income. And at the year of 3, we achieve a positive cash flow, so that we can say our payback period is at the year 3. And until the year 15, we have achieved a cumulative cash flow of 500 million.
In conclusion, 96,727 tons of ammonium sulfate and 321,938,000 of methanol is produced yearly. A 99% of sulfur dioxide and 98% of carbon dioxide removal is achieved from our plant design. 81% of utility is reduced through heat integration. The total capital investment that is required for this plant is 88,782,386.17 cents. The rate of return of the plant is 38%, which is higher than the minimum rate of return. Lastly, the payback period that occur will be in the 3rd year of the plant operation. That is all from our group. Thank you.